All right, so in this video, we're going to talk about area between curves. And you've seen a lot of this before, kind of in passing almost, as we built up the definition of area using the Riemann sum. So if you've put in the work prior, then hopefully now it's all going to kind of come together. So what I have up on the screen so far is just your standard area under the curve type problem, where we have our areas defined as the integral from x equals a to x equals b of the function dx. Remember, an integral adds up a bunch of really small things. And so we've got those rectangles under there. We're trying to come up with infinitely many of them, and we're going to sum up their areas. In terms of the actual rectangle itself, just as kind of a reminder, this was your base dx, and this was your height f of x. So we've got a base times a height, as we will in all of these other problems as well. So that's really just an area under the curve that I have drawn up there. When it comes to area between two curves, I'll go ahead and I'll sketch now a top function that looks something like this and a bottom function that looks something like that. So if we truly want the area between these two curves, let's say this is again A and B, and this is the area we want. Okay, I'm going to label the top function T and the bottom function B. You'll hear me say this a lot. We've got tops and bottoms, we've got lefts and rights. And so in this particular case, we have a top and a bottom. So if I want to find the area of that shaded region, it really wouldn't be any different than me wanting to find the area of, let's say, this shaded region here. I would just take the area of the square minus the area of the circle, which is ultimately the area of the big minus the area of the little. And that's the same thing here. The area of the big would be all of this right here. And then I would want to subtract out the area of the little. So as I write this now, our area would be the area of the big, so I'll say a top dx, minus the area of the little, which would be our bottom dx. Now, we wouldn't need to compute this as two separate integrals because we're both with respect to x and we're both on the interval a to b. We, of course, would want to simplify this down now to one single integral from a to b, top minus bottom dx. So area between two curves with respect to x will always be found by taking the top minus the bottom on that interval a to b. Okay? Now, there is also another option. Let me go ahead and erase this right here. The other option is now going with respect to y. So now when I draw my picture, I'm going to draw it a little differently to where maybe I'll have this guy and I'll have this guy here. And if we want the area between these two curves, let's say right here, then we would want to focus on dy instead of dx. Okay? If we're focused on dy, then these values are going to need to be y values. So maybe I'll call this one c and I'll call this one d. And then labeling the functions, we would say this is a right and a left. Now, in theory, if you take the screen and you turn it to the right, it's pretty much the same picture as this right here. So what I'm about to go through isn't any different. I would take the area of this big minus the area of this little. In our case now, it would be the area from C to D. The big would be our right, dy. Again, I know it's got to be dy because C and D are y values, minus the area of the little on C to D, which would be L dy. And putting it all together, just like the with respect to x, we would have the integral from c to d, right minus left, dy. Now, deciding on dy versus dx many times depends on the problem, and so we're going to look at a couple different examples here, but remember, what we're doing here really isn't anything different than you've done in the past. We're taking it a little further with some basic geometry, I suppose. But just get in the mindset of hearing me say a lot and think yourself thinking a lot of top minus bottoms, right minus lefts, and that'll get us going at least to where we need to start. Okay, so with this example here that we're going to start with, we're going to find the area that's bounded between this parabola and the x-axis on the interval 0 to 2. So the first thing you want to do here is start with a graph. So I know that the original graph is the parabola shifted down 1 unit. So if we take a parabola and we shift it down 1 unit, we get something that looks like this. That's at -1. And we're interested in the area bounded between it and the x-axis on the interval 0 to 2. Well, I know because of how x-intercepts work that this has got to be a +1, therefore a +2 would be next to it. So when I look at my area, I've actually got two different parts. I've got this part here, and I've got this part here. Now, I like this example because it relates back to the things we've talked about in the last chapter, where area below the x-axis would be negative and area above would be positive. But if we stick to that top minus bottom mentality, it's all going to take care of itself. Let me show you what this looks like. So the area here would need to be these two separate regions added up. The first region, let's go 0 to 1. Okay, so from 0 to 1 would be this. The top function, and a lot of times you'll see me draw these in here. If you draw a vertical line in there, where that top touches and that bottom touches, that's going to tell you which function you're on. So for this first one, the top is the x-axis. In other words, y equals 0. So we would have a 0 minus the bottom. The bottom is the x squared minus 1 dx. And so for this part, again, area below, if we would have just computed from 0 to 1, that integral, we would have got a negative area. But because now we're viewing this as a top minus bottom, the 0 minus is going to give us a double negative, creating a positive area for that region. Okay? And then moving on to the next one, we would have a plus because we're adding the areas, the integral from 1 to 2. And if I put this vertical line in here, you can see the top now would be the x squared minus 1, and then minus the bottom at 0 dx. Okay? So again, just kind of following me here, from 0 to 1, we've got our top minus the bottom, and then from 1 to 2, we've got our top minus the bottom. Now that you've got it set up, you could compute both of these separately. I'm not going to do that. I think you guys can handle that since you've just completed that chapter. This first part gives us a 2/3. The second part gives us a 4/3 for a total area of 2 in this particular problem.